Hi everyone, myself Sunil Mandal. I am a PhD scholar of NITK Surathkal. I am working under the guidance of Dr. Pujo Prabhakaran. My paper title is A Novel Bidirectional High Gain DC-DC Converter with Active Switch Inductor with Wide Voltage Conversion Ratio. My content consists of introduction, where I will be discussing around about high gain DC-DC converter in detail, like isolated, non-isolated, and non-coupled, so on. And then background and motivation. What actually motivate me to develop novel high-gain DC-DC converter, bidirectional DC-DC converter, and then I will be discussing about post-converter derivations and the features of the proposed topology, operating mode, steady state analysis, specification and closed loop control, simulation result, followed by conclusion and future work. Introduction. Bidirectional step up, step down converter are gaining popularity and used in a numerous modern power law tuning based systems like electric vehicles. Suppose electric vehicles, battery level voltage and machine level voltage is not matching, then high gain DC-DC converter is basically useful for this application. And energy also, in case of regenerative case, energy also can be stored in a battery. uh, B microgrid. In case of DC microgrid, if some voltage drop happen in the DC microgrid, that time also bidirectional converter is very useful for boosting the voltage. And in normal cases, in the DC microgrid, it will store the energy in the battery, so it's a very useful. And it is suitable for UPS, island renewable energy system. So this is a typical diagram of two state energy flow. Introduction. I'm continuing. Bidirectional DC-DC converter can be categorized into two types: isolated and non-isolated converter. Isolated converter are preferred where the galvanic isolation and high voltage gain is required. In case of isolated converter, primary and secondary can be separated by using isolated galvanic isolation. And main advantage of isolated converter is voltage gain of the converter can be increased by just changing the number of turn of the transformer. But it has several disadvantages, like it increase the size and cost of the system, and because of large, it require large space, and losses will be more. It will suffer voltage spike due to the leakage inductance. Relatively, there will be low efficiency and results in high voltage test across the switches. So far as non-isolated high-gain DC-DC converter is concerned, it is suitable for simplicity and low-cost application. It has also some drawback, like it can't provide galvanic isolation, and conventional non-isolated converter have limited voltage gain. Non-isolated converter also can be categorized into two types: coupled inductor type, non-coupled inductor type. Coupled inductor type is preferred where the high voltage gain is required. And here, performance will be similar to isolated converter, but uh, efficiency will be better, and losses will be less compared to the isolated converter. So drawback will be same as the isolated converter. So far as non-coupled conductor type is concerned, it is preferred for simplicity and low cost applications. And it has also some disadvantage, like it can't provide galvanic isolation. And in case of Conventional non-isolated converter have limited voltage gain, background, and motivation. To overcome the drawback of isolated converter, a high gain non-isolated DC-DC converter can be utilized. Some existing high gain bidirectional non-isolated non-coupled inductor based DC-DC converter with voltage boost capability in one power flow direction and voltage buck capability in other power flow direction are listed below. As it can be observed, there are four topologies: A topology is A, B, C, and D. Topologies in A, voltage stress across the switches is less, total number of component is less here, voltage gain is very high in both bucking as well as boosting mode. Sorry, voltage gain is low, very low here in as both bucking as well as boosting mode in the topology A. And topology B, it is published in 2020, and good voltage gain in both buck as well as boost mode. Total number of components is less, but maximum voltage stress across the switches is very high. And author has used very large number of switches here to develop this topology. Topology in C, it can be observed voltage stress is less here, and author has incorporated only two inductors to develop this topology, and but author has used large number of switches to develop this topology. Still, voltage gain is limited in case of boosting mode, and total number of components is very high here. Topology in D, ultra voltage gain bidirectional DC-DC converter. It is published recently in 2022. Voltage gain is very high in both bucking as well as boosting mode, and maximum voltage stress across the switch and diode is very high, and the author has used very large number of components to develop this topology. Number of switches is very high, maximum voltage stress across the maximum voltage stress are very high, background and motivation. In continuation, observation from the literature survey, in there are numerous converter with the very high voltage gain, but is achieved using large number of components. Somewhere voltage gain is good, but voltage stress across the switch and diode is very high. Somewhere voltage gain is good, performance is good, but efficiency is very low, and it will provide limited range of duty ratio. So these are the disadvantage. So conclusion from the literature survey, a high gain bidirectional DC-DC converter with less number of switches and intermediate capacitor, low component stress, and simple control structure are not commonly found. To overcome the above mentioned issue, a novel bidirectional high gain DC-DC converter with active switch inductor and wide voltage conversion ratio is proposed. I have proposed one topology, and how I have driven this topology. So I'm going to explain here. This is my previous topology, and I have proposed this already, and I have developed this topology for getting high voltage gain. So this is also bidirectional, and as it can be observed here in this part, I have incorporated here active switch inductor, and still voltage gain was less here. So in place of active switch inductor, I have put here interleaved structure, and with check converter. This part is check converter, and this is interleaved structure. And the advantage of interleaved structure is it will reduce the input current ripple. and the voltage gain of this converter is high, but still it is limited. So to achieve high voltage gain, I have developed this topology, and before that, I have modified this topology with this. So here component is less. I have removed S2 switches. Here I have removed S2 switches and L2 as it can be observed here. But still the voltage gain is equal compared to the previous topology. And I just wanted to say voltage gain of this topology and this is voltage gain of this topology and this is equal, but still it is limited. So to achieve very high voltage gain, I have developed this topology, and how I have developed this topology. So I have incorporated again here active switch inductor as it can be observed. Remaining part is same, so it can give very high voltage gain, and it is suitable for electric vehicles, DC microgrid where charging and discharging can be done. So it's suitable for those applications where charging and discharging can be done very high voltage level. This is the proposed topology, and I have just incorporated here active switch inductor with the modified Jetta converter, and there are many features in this converter. It provide continuous input current, voltage stress across the switch and diode is very low here, and it support bidirectional operation, buck mode in one power flow direction and boost mode in other power flow direction, and it will provide wide voltage conversion ratio for both bucking as well as boosting mode. Control structure is very simple. I have used only a few number of component, three intermediate capacitor and four inductor to develop this topology. This is operating mode. During on mode, all the inductor store energy, and during off mode, all the inductor will release energy. This is a steady state waveform, the proposed converter. When converter is flowing from low voltage to high voltage, it can be represent M12, so VDC1 to VDC2. Then voltage gain can be achieved 1 plus 4D by 1 minus D at this is a voltage gain formula, and when converter is operating in VDC2 to VDC1 mode, and I mean buck mode, then voltage gain can be found at dx by 5 minus 4 dx, and this is a voltage gain versus duty ratio plot for both bucking as well as boosting mode. M1 to denote the boost mode and M21 denote the buck mode. So performance of the proposed bidirectional DC-DC converter is very good, as it can be observed in this voltage gain versus duty ratio plot. This is a steady state waveform, the proposed converter. As I discussed earlier, during on mode, all the inductor store energy. During off mode, all the inductor will release energy. And this is a diode current waveform. And this is a s- capacitor C10 and C20 current waveform. To validate the efficacy of the proposed converter, it is simulated and designed taking the power rating of 500 watt, switching frequency 20 kilohertz, VDC1 input have chosen 48 volt, VDC2 output voltage will come around 284 or nearby 300 volt. I have designed in open loop taking the duty ratio of 50%. And this is a closed loop schematic diagram of the closed loop. This is for voltage control. This is for current control and voltage control. And here I have I have compared the actual signal with the reference signal, which will generate error. That error is passed through the compensator that will generate DT ratio, and that DT ratio can be utilized for turning on and turning off the switches of the plant. Plant is nothing but the high gain DC-DC converter. Closed loop control. Proposed converter is modeled using a state space averaging and small signal modeling. Both current control and voltage control is possible here. For current control, type 2 compensator is used. For voltage control, type 3 compensator is used. Uh, Cutoff frequency for the current control is 2 kilohertz. It is generally considered one fifth to one tenth of the switching frequency. And for voltage control, I have chosen cutoff frequency 500 hertz. Generally, it is considered greater than RHP 0, and desired phase margin I have chosen 55 degrees. This is the uh, Bode plot of the compensator open loop transfer function with current control. This is for current control and this is for voltage control. Simulation result. This is a simulation result of the proposed converter, and when converter is operating from BDC1 mode to BDC2, I mean boost mode. So this simulation result can be observed. So during on mode, all the inductor store energy. During off mode, all the inductor release energy. As I talked earlier, also this is a diode current waveform. This is the capacitor current waveform, and here it can be observed. Post converter can achieve desired output voltage, which is around more than 200 volt. I mean 300 volt. Input is just 48 volt, and this is input current, output current, which is yeah, yeah, wait. Mm. This is a simulation result, and I have uh, done also closed loop for the current control, and here it can be observed ref, mm, uh, actual current follow the reference current properly. This is a conclusion. A bidirectional high gain DC-DC converter is proposed, which is suitable for charging, discharging the battery. Proposed converter support bidirectional operation in demonstrate low voltage stage component. Proposed converter demonstrate wide voltage conversion ratio for both bucking as well as boosting mode. Proposed converter was designed and analyzed in the for the power level of 500 watt. Closed loop controller are designed to operate proposed converter in voltage and current control mode. Detailed simulation are also presented to validate the theoretical design and efficacy of the proposed converter in open loop, closed loop as well as open loop. Proposed converter found to be suitable for electric vehicles, AVs, microgrid, etc. and so on. This is my future work, and these are the references. Thank you, everyone.